I'm Joshua Benabou. I'd like to tell you about our recent work on the cosmological dynamics of string theory axion strings. This is work with Quentin Bonnefoy, Ben Safdi, Malte Buschmann, and Soubhik Kumar. In this work, we investigate the properties of axion strings associated to string theory axions arising as the zero modes of higher dimensional gauge fields. This is a contrast to axions arising from field theory constructions. We are interested in computing the tension of these strings, understanding their formation mechanism, their cosmological dynamics, and their observational signatures. First, let me quickly review field theory axion strings. So field theory axions are realized as the Goldstone bosons of a global U1 Pachequin or PQ symmetry broken at some high scale Fa. They are described by Lagrangian of the type shown here, expressed in terms of a complex scalar field phi, the PQ field, whose complex phase is identified as the axion. If the PQ symmetry is broken after inflation, then we generically obtain axion strings, which are one-dimensional topological defects of the PQ field, characterized by the property that any one-dimensional contour enclosing the string has a non-zero winding number for the axion on that contour. A notable problem with field theory axions is the so-called PQ quality problem for the QCD axion, which is the requirement of a very high-quality global U1 symmetry to ensure that the dominant contribution to the QCD axion mass is from QCD instantons, which is difficult to realize given the quantum gravity expectations that global symmetries are ultimately violated. On the other hand, string theory axions, which come from the zero modes of higher dimensional gauge fields, have a shift symmetry which is protected by the higher dimensional gauge invariance, and thus the PQ quality problem is naturally mitigated. We begin our study of the stringy axion strings with a toy extra-dimensional axion construction. We consider a 5D U1 gauge theory with the fifth dimension compactified on an orbifolded circle and the four-dimensional axion defined via the gauge invariant Wilson loop. The size of the fifth dimension here is parameterized by the gravitational degree of freedom here, the radion, and by solving the equations of motion of the axion-radion system, we're able to compute the tension of these strings. We find that if the extra dimension is flat, then the tension of the string is parametrically Fa times m Planck, whereas if it is warped, the string tension is parametrically Fa squared with a logarithmically divergent piece divergent in the IR, just as in the field theory axion case. We also find that the string tension is concentrated in a region much smaller than a Planck length around the string, which suggests that we must go beyond the axion-radion EFT to accurately resolve the string core where the EFT breaks down. In fact, as we discussed in our paper, in string theory, the axion strings discussed previously may be realized by wrapping branes around cycles of the compactified volume of, for example, a 10-dimensional string theory. In our paper, we compute the tension of these wrapped branes and find the same parametric result as from the 5-dimensional EFT. We then turn to the question of formation of these axion strings. We find that in generic inflationary contexts, these axion strings do not form. However, in certain exotic scenarios, such as deep brane inflation, they may indeed form. If they do form, and if we obtain a network of QCD axion strings, we compute that the strings emit too much axion dark matter, unless the QCD axion arises from a strongly warped cycle. Another way to avoid the overproduction of QCD axion dark matter here is if the axion sourced by the string is a linear combination of the QCD axion and other heavier axions. In this scenario, which is inspired by the Axiverse, we find that the QCD axion may indeed constitute the dark matter. Further, if the axion arises from a flat extra dimension, then the large string tension leads to strong gravitational wave signatures relative to the field theory case, with gravitational wave signatures that could be probed by future observatories such as the Einstein telescope or the Big Bang observer. In summary, in this work, we find that string theory axions do not generically form axion strings, though if they do form, the string network overproduces the QCD axion dark matter abundance, unless there is warping, or if the axion sourced by the string is a linear combination of the QCD axion and other heavier axions. The key takeaway of our work is that we demotivate the so-called post-inflationary axion scenario, which does not generically arise in string theory. And on the other hand, we motivate the continued search for the QCD axion over a broad mass range. Thank you, and we hope that you'll check out our paper.